So in this video, we're going to look at a problem. We have an object at temperature 80 degrees Fahrenheit and we place it in a medium that's held constant at 45 degrees Fahrenheit. So obviously this thing's going to cool off and to cool towards a temperature of 45 degrees Fahrenheit. 10 minutes later, we measure its temperature and find that it's dropped to 72 degrees Fahrenheit, and we're asked to determine an equation for the temperature of the object as a function of time. So this is clearly a Newton's law of cooling problem. Remember that Newton's law of cooling tells us that the rate of change of the temperature with respect to the time is proportional to the difference between the temperature of the object and the temperature of the medium. So to say that it's proportional, the difference means that it's equal to some constant times it, and we're going to do, for convenience, is we're going to decide that we want K to be greater than 0. So let's think about this for a moment. If the temperature of the object is greater than the temperature of the medium, like in our case, then the object should be cooling, and dt over dt, change in time with over to time, should be negative. We know this is positive because the temperature the object is greater than the medium. We know K is positive, so this product would be positive, whereas we want to put a negative derivative. So let's put a minus sign in here. And then let's ask ourselves, what if the temperature of the object less than the temperature of the medium? Then this would be negative. We'd have a negative times a negative, and our rate of change would be positive, which would make sense if our object's temperature is less than the object of the medium. Then the object should be warming up. So here's our model, the Newton's law of cooling, and so let's go ahead and put what we know in there. So what we know is that, well, we have dt over dt equals, we don't know this K that will be dependent on the material that these things made of. Well, we'll be used the 72 degrees Fahrenheit to find out the temperature of the object. Capital T is a variable that the temperature of the medium is held at 45 degrees. And we also know that the temperature at time 0 is, the T of 0 is 80 degrees Fahrenheit. So here's our initial value problem. So we want to solve that, we can solve it by separation of variables. You can also solve this using an integrating factor. Let's solve it by separation of variables this time. So what we'll do here is, we have dt to separate the variables. We multiply both sides by the differential for time, so we'll have little dt over here, and we divide by the temperature minus 45 to get this capital T over there with dt. So we end up with dt change differential for temperature over capital T minus 45 equals to negative K dt differential of time. And so we then integrate both sides of this, and since that K is constant, we bring it out at an integral. So let's have a negative K with respect to time, this side over here. Since the number in front of capital T is 1, simply this turns out to be just a natural log of the absolute value of T minus 45. And the right side, we have negative KT, and we have plus C on both sides. But as usual, we bring the constant from this side over here, so we only need the constant on this side. Now, if we think about this a little bit, for our situation, capital T is always greater than 45 degrees. So we don't need those absolute value sign. So we just have the natural ln of capital T minus 45 equals to negative KT plus c. And now to get rid of the natural log, we exponentiate both sides. So we have e to the log of the capital T minus 45 equals e to the minus kt plus c. And over here we can split this into two separate parts. We have e to the minus kt and e to the c. Over here the exponential and the logarithm cancel each other, so we have to minus 45. We have t minus 45. That's because those are inverse functions of each other. Of course, this is e to the c is some other constant, which I'll be sloppy and just call c. Again, although this is not the same, e to the minus kt equals to t minus 45, or t, that's, I add to both sides, t is 45 plus c e to the minus kt, so that the solution to our differential equation. Notice it has two constants in capital T and negative and little k here, and we can find capital C by using this initial condition. So the temperature at time 0 is 80. If we put 80 in for the temperature and 0 in here for the time, when it puts 0 on the time, this becomes 1. So we have 80 equals 45 plus C. So we subtract 35 from both sides. We find C equals 35. So that means our equation then looks like T equals 45 plus 35e raised to minus kt. Now to find k, we put in 72 for our temperature and we go with time. Here put our information was given in minutes, so we'll assume little t is in minutes. So at this point, then we've got 72 equals 45 plus e 35. We're gonna put 10 in for t, so we have e to the minus 10k. We can construct 45 from, we can subtract 45 from both sides. Then let's see what's gonna be 32 minus 5, so that's 27 equals 35e to the minus 10k. We'll divide both sides by 35, so 27 over 35 equals e to the minus 10k. We take the natural log of both sides to get rid of this e. So we have natural log of 27 over 35 equals negative k. So k equals the natural log of 27 over 35 divided by negative 10. And let's calculate it, an approximation for that. So our k is 0.02595. So our final equation for the temperature of the object as a function of time will be T is equals to 45 plus 35 multiplied by E raised to 0.02595 multiplied by the time.
Hi, in this video, we're gonna solve the Euler's equation using MATLAB. First, we should set the symbols of y and t. Next is we're gonna input the step size of the equation, or the h. In here, we're gonna use 0.1. Next is we're gonna input the equation that we're gonna use. In this part, we're gonna use the equation 3 times cosine t minus 2 times y. Next is we're gonna input the t sub 0 here in our equation. In here, we're gonna use t sub 0 of 0.1. Next is we're gonna input the y sub 0 in this equation. The y sub 0 that we're gonna use is 0. Next is we're gonna input the last t value in this equation. Here we're gonna use 0.4. Next is we're gonna input the solver of this equation, or the Euler's equation, and enter. In here, we could see the values of the t sub n, y sub n, and y sub n plus 1. So this is how we could solve the Euler's equation using MATLAB.